In this video, I'm going to go through what happens in a circuit when you put cells in series or parallel. This will use Kirchhoffs Voltage Law and Current Law. I've made a separate video for resistors in series and parallel. It is part of topic 5.2 of the IB Physics Syllabus, so it's relevant to both SL and HL. Please take a moment to read the success criteria for this video. Okay, so first of all, let's just remind ourselves of what Kirchhoffs laws are. So the first one means the potential difference around any continuous loop is going to be zero. But I also think of it in another way. We can also think of it as the total potential increase will equal the total potential decrease. And in this case, I'm talking about the potential energy. So if we go around any loop, here we have a cell. I call that a potential increase. I'm giving the electrons some energy. And as I go around my circuit, I come to a load, in this case a resistor. In that case, I'm going to use all that extra energy that I was given from this cell. And when I get back here, I'm going to be back to where I was at the beginning. Now this is a potential, so we're not necessarily saying when it gets back here it has zero energy. It just means that all the increase in energy, and if you remember, potential difference or voltage is measured in volts, but that's hidden inside as a joule per coulomb, energy per charge. So all the energy per charge that's given in the circuit gets used up in the actual circuit itself. So it's like gravitational potential energy. You determine where your H equals 0 is, or you measure your relative heights. Same here. So in any complete loop, which I have here, the potential increase will equal the potential decrease. Let's look at the second one. It says that the sum of all the current going into a junction equals 0. Here's another way to think about that. The total current going into a junction equals the total current coming out. Remember, current is related to the number of electrons, because current is the amount of charge moving past a point per time. So if I have a certain number of electrons coming here, let's say I have 10 electrons coming in, I have to have 10 electrons coming out. This is just using the conservation of charge, whereas the voltage one uses the conservation of energy. Okay, so let's see what happens when we start to put cells in series. Now in this first one, you can see I've got a diagram here, and I have the potential difference before and after the resistor. Now, since wires are perfect, I hope you realize that that's actually before and after the cell as well, because I only have the two things on my circuit. So this voltage is going to be the voltage that's happening across my cell. And I'm using a cell that has 0 internal resistance. If you don't know what that is, don't worry, it's in another video. Okay, so I have here that my voltage is 9 volts. That's the voltage that's being given off by my cell. And you can see I have a current of 9 amps. So what I've done in the second picture is I've used the simulation from the FET simulation site, and I've put 2 identical cells in series. So these electrons that are here are going to go through, and they're going to be given 9 volts of energy. Remember, volts are just joules per charge. So they're going to get 9 volts here, and those same electrons are going through the second cell as well. So what happens? They get some more energy. And you can see that my voltage now has 18 volts, twice as much as it used to have. Now I also have here that now I have my current is doubled. So you might say, well, wait a second, my cells have just gone and changed the voltage. Why has my current changed? Now for that, I want you to go back and remember Ohm's law. R equals V over I. If I move this around, I have V equals IR. And I like to put it in that form because it's easier for us to relate the current and the voltage. Now, when I have this, I have doubled the voltage, but I have not changed the resistance. That's the same resistor in my circuit. So the current has doubled because it's directly proportional to the voltage. Okay, so let's move on and see what happens when I put them in parallel. So first of all, this is the exact same circuit that I've been using before, and I've just copied it onto this page. What I've done in the second picture is you see now that I have two cells and I've got them moving in the same direction. That's really important. We'll talk about what happens if they're not in the same direction later. So again, I have the potential difference across my resistor here. Remember, that would be the same as across both of the cells. So it's the same, even though it's marked here, that's the same as putting it here and here, before and after the two cells. So if you see in this case, my voltage is actually exactly the same as what it was when I only had one cell. Now, hopefully that makes sense. Let me just mark out again what it looks like if I go around this circuit. So let's say I start here with an electron. It's going to go here and it's going to go down towards my resistor and back again. If I then look at the other one, I'm actually going to have an electron starting here. It's going to go down, it's going to go to my resistor and back again. Notice now that my electrons actually don't go through both cells. They only go through one cell, which is why they only pick up 9 volts of energy. Remember, joules per charge. One thing that is different though is look at the current. I have 0.9 amps here, and there is actually only 0.45 amps in this branch up at the top. Remember Kirchhoff's current law. It says that the total current going into a junction equals the total current coming out of a junction. So if I look at this junction right here, I have 0.45 amps from the top cell and I have 0.45 amps from the bottom cell coming in to create this 0.9 amps. In this case, I have two different paths causing my electrons to go through. So this means I have the same voltage or potential difference in my resistor, but I've doubled the amount of current going through it. This is a different result from before when I had cells in series. Remember, that doubled the voltage and also doubled the current going through it. In this case, the voltage is the same and the current is the same. We'll talk later in this video about why you would actually put two cells in parallel. Okay, so what if the cells are in opposite directions? Stop and make your guess first. I'm going to do the one in series. Have you come up with an idea? So here it is here. I have my two cells in series and I put them in opposite direction. So remember Kirchhoffs Voltage Law. The total potential increase equals the total potential decrease around any loop. And so in this case, since I have the cell, let's say this one's the increase because it's the same direction I had last time. In my loop, here's my potential increase, that would be 9 volts. But, oh wait a second, right here I have it the opposite direction. So right there is a potential decrease I'd be causing my electrons as well. So combined, these are now have no potential increase or decrease, which means there's no energy given to the electrons to make them flow through the circuit. I have 0 voltage then and 0 current. Will that be the same if I put them in parallel? Stop and have a think. Oh my, this is what the PhET simulation actually gives me. It gives me this big sign here of a fire. What do you think that implies? It implies that basically my current is going around like this. You can see the little message down at the bottom, animation speed limit reached. In other words, they can't show me the electrons moving around fast enough anymore. But wait a second, why are they doing this instead of coming down here to my resistor at the bottom? Well, let's consider an electron coming from this end right here. When it gets to this junction, it could either go down or up. And why would it go up rather than down? Well, remember, this is like having two parallel branches. So instead of thinking as this being the center point and I have two branches here, let's change our thinking for a second and let's say this is our original and I have two branches, the cell and the resistor, off of this one branch. Well, this is going to have very minimal resistance in comparison to the resistor. So electrons are going to be more likely going to this way. Now you might say, well, wait, that's another source here. The electrons can go in this direction because these are oppositely charged ends of the cell. If the cells had been pointing in the same direction, then our electrons would not have gone from the gold end to the other gold end. In that case, they would have to have gone through the resistor. So with minimal resistance, then we will get electrons doing this through our two sources, and that's why the more current going through, we're going to get it hotter and hotter, which is why they've got the little flames there. So let's go through a few different kind of questions. So 3 identical cells are connected in parallel to a resistor. What is the advantage of this? Well, let's go through and check this out. First of all, each cell produces more energy. Well, energy, remember that should be related to the volts, the amount of volts or joules per charge, and well, it's not going to change the number of volts that each particular cell can produce. So we can cross that off our list. Each cell supplies more charge. Well, remember charge, that's going to be related to the current. The amount of current is charge per time. Now, when I had them in parallel, did that cause the current to increase? No, in fact, it stayed the same. Each cell takes longer to run down. Now we're getting closer. If you remember, each cell that we had, even though the total current was still the same, each cell was only 0.45 compared to the total of 0.9. So what actually is going to happen when you put your cells in parallel, it's going to produce the same voltage, but it's going to draw a smaller current from each of the cells, making them last longer by still providing the amount of current that you're looking for. The total electromotive force is larger? No, because it still is only 9 volts. The difference between your potential difference and the EMF will be talked about in a separate video. So what I have here is the answer is C. Okay, 2 cells with 3 volts and 1.2 volts with negligible internal resistance are shown in the diagram. And there are 2 resistors of 9 ohms and 18 ohms, and you can see that they are connected here in parallel. What is the current in this 9 ohm resistor? Now, the first thing I want you to do is take a really close look at these 2 sources. Notice that the long, then short, now this one's short, then long. It means that they are connected and they're in opposite directions. Now I still am going to get a net result here, and it's going to be 1.8. So my total potential difference will be 1.8. Now the resistors are in parallel, so we're going to have to calculate the total resistance. Remember, since they are in parallel, I need to use this formula. And it's going to have to be easy if I'm going to be able to do this without a calculator. So that's going to be 1 over 9 plus 1 over 18. Yep, this should be straightforward. It'll give me 3 over 18, or my R total is going to equal 6. Okay, now with Ohm's law, we can calculate what the current's going to be. And there we go, 0.3. Alright, so that means there's going to be 0.3 amps of current in total coming from here. Now remember, we have 2 resistors and one is twice as big as the other. So which one will get more current? The one with the smaller resistance. And they're going to separate in the same kind of ratio that we have here. So if I then say, if I have 0.3 here, I'm going to get 0.2 and 0.1. So my answer is here, B. Okay, one more example. I have 2 cells X and Y connected in series with a resistor of 9 ohms. Okay, now it gives us some information about the cells. Cell X has 1 volt and it has an internal resistance of 1 ohm. If you don't know anything about internal resistance, I have another video on that. But for now, what I want you to realize is, let's think of it as having an internal resistor right here in series. Same with this one. And for Y, it tells us that it is 2 volts and also 2 ohms. So let's think about this. Notice that if I go around in my loop, these cells are actually backwards to each other. So my total voltage for the cell is actually only going to be 1 volt, not 3. Another thing then is I need to look at the total resistance. And these are in series, so all I have to do is add them up. 1 ohm, 9 ohm, 2 ohms, 12 ohms in total. Okay, so Ohm's law, to find out my total resistance, that will be 1 over 12. Now, if you don't, because you have to do this without a calculator, if you don't know what 1/12 is, don't worry, but you know that that's smaller than 1/10, right? And C is 1/10, so the answer that's smaller than 1/10, it's going to be D. I hope this video has helped you understand what happens when you put cells in combinations and to use Kirchhoffs laws to help solve the circuit problems.